Watch this. I'm going to ignore every pivot value. Sounds impossible, right? Yet this solution works perfectly. Want full solution? Check this video.
Hi everyone and welcome back. Today we are solving the lead code problem partition array according to given pivot. The problem gives us an array of integers called nums and a pivot value. Our goal is to rearrange the array so that all the element smaller than the pivot comes first, and then all elements equal to the pivot come next, and finally all the elements that are greater than the pivot come last. But there is an important condition, which is the relative order. The relative order of element within each group must remain exactly the same as in the original array. So this is not just a sorting problem. We must preserve the original ordering. Let's look at an example. Imagine that we have the num array, looks like this one, and the pivot value is 10. So the elements that are less than the pivot are 9, 5, and 3. And the elements that are equal to the pivot, 10 and 10. And the elements that are greater than the pivot, 10, are 12 and 14. And combining these groups give us the output array where the 9 and 5 and 3 came in the same order they appear in the input array, and then followed by the pivot values, and finally followed by the greater value also in the same order. So as you can notice that inside every group, the order remains unchanged from the original array. Now let's think about how to solve this. The first observation is that the final answer consists of three sections. A section that contain all the elements smaller than the pivot, and a section that contain all the elements that equals to the pivot, and a final section that contains all the elements that greater than the pivot. So while traversing the original array, we can collect the smaller and the greater elements separately. So let's see how we can do this in the code. First, we'll start by getting the size of the array. I'll define a variable n that will equal to nums.size. Then I'll create two vectors, one called smaller and another one called greater. This vector will store all the elements that are less than or greater than the pivot. So two vector integer, let's call them smaller and greater. Then we will iterate through every element in the array, and for each element we check three possibilities. If the element is smaller than the pivot, we push it to the smaller vector, and if the element is greater than the pivot, we push it into the greater vector. So for auto element in nums, we check if the element is less than the pivot, and in this case we push it to the smaller array vector. And the same, if the element is greater than the pivot, we push it to the greater vector. And notice that we don't explicitly store elements equal to the pivot. And this is a clever optimization. Instead of storing them, we will calculate how many pivot values should appear later. So after the loop, I'll define, first I'll get the size of the smaller vector, and the smaller vector now contain or every element less than the pivot, and the greater vector will contain every element greater than the pivot. So we need to determine how many pivot values should exist in the original array. We already know the total number of elements in the original array, which is n, and we know how many elements are in the smaller vector and how many elements in the greater vector. So the number of the pivot elements must be n minus m minus greater dot size. You maybe wonder why I defined the or getting the size of the smaller array here and not the greater vector, and you will know the reason in just a second. After that, we will loop for int I equals 0 and I is less than the number of pivots and plus plus I. Then I will use the smaller vector as our final output vector. So we will push directly the pivot to the smaller vector. So again, here we have the number of pivot values, and we use the smaller vector as our final output vector. So we pushed as many pivots to the smaller vector. At this point, the smaller vector actually contains two sections. First, the element smaller than the pivot, then all the pivot elements. And this will map to, in our example, here, now the smaller will contain this section. Now, we only need to append the greater element. That is exactly what the insert operation does. So we will call smaller dot insert, and we need to insert at the end of the smaller vector, so we give it the end iterator, and we need to add the whole greater vector, so we give it the begin iterator and the end iterator, and finally we return our smaller vector. So now our smaller vector will map to the required output based on our example. So let's run it to make sure we don't have any syntax error. Let's submit it. And now let's analyze the complexity. We iterate through the array once, and that takes O of n time. Then we append the pivot values. The total number of pivots values can be at most n. So this step is also O of n. And finally, we inserting the greater element takes time proportional to the number of greater element, which is also at most m. So the overall time complexity is O of n. For space complexity, we use two additional vectors. Together, they store all the elements except the pivot values. So in worst case, they may store almost all the elements of the array. Therefore, the space complexity is also O of n. What I like about this solution is its simplicity. Although there is some other solution where you can solve this problem without defining any extra vectors or spaces, you can solve the problem in place without any extra spaces. Uh, but it's a bit complicated pointer manipulation. We don't need sorting, and we automatically here preserve the relative order of the element because we add them to the vector in the same order as they appear in the original array. So again, here's the key idea. We collect the smaller element, we collect the greater element, we compute how many pivot values exist, and then we append the pivot values and then append to the greater elements to the smaller pivots, to the smaller vector. And finally, a clean and efficient linear time solution. If you enjoyed this explanation, make sure to like the video and subscribe to the channel. And let me know in the comments how you solve this problem. Thanks for watching, and I'll see you in next video. Bye.